Hi, my name is Chi-Jung.
And my name is Ruidong. We are from the Sci-Fi Lab at Cornell University. We're excited to introduce EchoWrist.
We want to thank all our co-authors, Devansh, Catherine, Vipin, Oliver, James, Sicheng, Boao, Mose, Francois, and Cheng. EchoWrist is a wristband that can track continuous hand poses. EchoWrist can also recognize hand-object interactions. These are all based on active acoustic sensing. As the primary interface for our interactions with the world, our hands play an essential role in our daily lives. We use our hands to support thinking, to facilitate communication, to perform intricate tasks, and to touch to explore our surroundings, and grasp to manipulate objects. Tracking our everyday hand activities can support a variety of real-life applications. For example, the Apple Watch now features a double-tap gesture that enhances the convenience by enabling users to control it with a single hand. What if we could enhance our tracking capabilities even further? Imagine having a significantly more powerful device, one that can monitor hand-object interactions with precision. Our AI agent could then offer contextual support accordingly, just like in this video, where the agent provides suggestions based on the user's activities. Hands are so important in our daily lives. To understand hand-related activities, researchers have explored different sensing techniques for wristbands to track hand poses and hand-object interactions. These techniques include IR, IMU, thermal cameras, depth sensors, and bioimpedance. These systems all provide promising tracking ability on a wristband. However, these devices are power-hungry, which leads to a short battery life. Also, they are obtrusive, which can cause discomfort when worn for extended periods. These issues make it challenging to incorporate these devices into our everyday lives. So, is it possible to create a wristband with the capability to track hand activities while remaining low power and low profile? We propose EchoWrist, an active acoustic sensing wristband. Using the single wristband, EchoWrist can continuously track hand poses. EchoWrist can also recognize hand-object interactions. With these capabilities, EchoWrist still operates at a low power, which can last 19 hours using an Apple Watch Series 8 battery. Moreover, with the thickness of just 6 mm, EchoWrist is minimally obtrusive. Since EchoWrist is low power and low profile, it could be easily integrated with commercial smartwatches and used in our daily life in the future. EchoWrist leverages a sonar-like technique. The speakers emit acoustic signal to the hand and object. If the hand or object is in the path of the sound waves, the sound bounces off the object and returns echoes to the microphone. We perform echo profile analysis on the captured signals. The generated echo profiles represent the distribution of reflection strength at different distances. Like in this video, when the speakers and microphone on the wristband move closer to or further away from the tumbler, we can see that the movements leave clear patterns on the echo profiles. Subtle movements can also be captured and reflected on the echo profiles. Different hand shapes and hand movements create clear and unique echo profile patterns that can be used to track 3D hand poses continuously. When the hand is interacting with some objects, the sound waves can also reach them, leaving distinct patterns on the echo profiles that can be used to recognize hand-object interactions. Leveraging the active acoustic sensing technique, EchoWrist features only 2 pairs of speakers and microphones, a customized microcontroller, and a battery, which is minimally obtrusive and easy to wear. The speakers and microphones are strategically placed at each side of the wrist to minimize the occlusion caused by the wrist and hand. To infer the hand poses and hand-object interactions, we used the customized CNN model with the ResNet 18 backbone. The model takes in the echo profiles and predicts the hand poses or hand-object interactions.
To evaluate EchoWrist's capabilities in understanding hand activities, we conducted 2 user studies. The first study investigates EchoWrist's performance in continuous 3D hand pose tracking, while the second study focuses on recognizing hand-object interactions. Now, let's look at the details of the study. In the first study on continuous hand pose tracking, we invited 12 participants. Each participant was asked to perform 5 simple gestures, which are bending 1 finger at a time, 10 complex gestures, which are the 10 numbers from the American Sign Language, and 3 wrist orientations, which are facing the palm in different directions. The participants were asked to perform each gesture 4 times in a session, and we collected the data for 20 sessions. In total, over 17,000 gestures were collected. With this dataset, we demonstrate that EchoWrist can achieve state-of-the-art hand tracking performance, meanwhile only requiring minimal training effort from new users, and is robust against different types of noises. To quantitatively measure EchoWrist's hand tracking performance, we used media pipe to acquire the ground truth of the hand pose and used 3 metrics. We calculate MJEDE as the average Euclidean distance between the predicted and ground truth coordinates of the 20 joints on the hand. MJAE focuses on the bending angle of each joint, such as the joint demonstrated here. In addition to tracking the position and angle of each joint, EchoWrist can also capture the orientation of the wrist, which is represented by the vector visualized here. We calculate MWAE, which is the angle between the ground truth vector and the predicted vector. Our results are very promising. EchoWrist achieves under 5 mm in MJEDE, or less than 4 degrees if measured by MJAE. To situate these figures to the visual performance, we have a video clip from a researcher. The average MJEDE of this video clip is under 5 mm. When recovering the wrist orientation, EchoWrist achieves an MWAE of under 7 degrees. The average MWAE of this video clip is under 7 degrees. The performance is great, but how much training data does a new user need to provide? We demonstrate that EchoWrist can work well even with a small amount of training data. When no data from a new participant is used for training, which means that the results are user independent, the MJEDE was about 12 mm and MJAE around 7 degrees. The MWAE for the wrist orientation is 17.5 degrees. With only about 1 minute of tuning data, which is less than the time needed to set up Face ID, the performance drastically improved. MJEDE falls under 7 mm, MJAE under 5, and the wrist orientation under 10 degrees. Even more, EchoWrist is robust against various noises. We experimented with 3 different types of injected noises. When injected with noise recorded in a cafe, which is over 70 decibels, there is almost no impact on the performance. Injecting louder noises of over 70 decibels recorded at a busy curbside or with music playing at the background, EchoWrist is still robust. Next, Let's look at how EchoWrist works in hand-object interaction recognition. We invited another 12 participants to conduct this second study. The participants were asked to perform commonly seen kitchen activities, including 6 dynamic interactions: pouring, twisting, peeling, drinking, stirring, and chopping. We designed another 6 static interactions, holding the bottle, cup, chopsticks, pot, kettle, and pan. 12 participants each finished 12 interactions with 4 repetitions and 5 sessions, adding up to nearly 3,000 samples collected in this second study. We achieved over 97% accuracy in recognizing these 12 interactions. More amazingly, EchoWrist still achieves over 80% user-independent accuracy when no data is provided from a new user. With the continuous hand tracking and hand-object interaction recognition capabilities, EchoWrist enables a variety of real-life applications. For instance, we propose a slide control application using hand pose tracking. Without a controller, we can easily control the slides using the wristband. We also introduce an interactive cooking assistant with hand-object interaction recognition. The assistant can track what the user is doing and provide suggestions accordingly during cooking. Thank you for watching.
For more details, please refer to our paper.